Mithun Shanbhag is my Twitter handle. Please feel free to follow me. Send me a LinkedIn connection request. Happy to connect always. Okay. That said, let's get the party rolling. Okay. All right. Okay. So this quiz application. So just to set some context here, it is a quiz application. It's a quiz it's a live quiz application that thousands and thousands of players can participate and play at the same time. These quizzes generally happen on Wednesdays, Thursdays, and Fridays at 5 p.m. And most of them are sponsored by companies like Microsoft. And you have multiple quizzes, and these quizzes form a tournament. So you win a quiz, you get some cash prize, you top the quizzes consistently, and you top the tournament leaderboard. You get an Xbox or an Apple Watch, depending upon who's sponsoring it. Okay? So again, the application is really used only few minutes in a week. Thursdays, Fridays, Wednesdays, Thursdays, and Fridays. And the duration of each quiz is about 20 to 25 minutes. We flash 15 questions. Each question has 4 to 6 choices. You lock an answer, and then after 30 seconds, after the timer elapses, we show the right answer and the statistics. Fastest finger first. So whoever answers correct first tops the leaderboard, right? Many people can answer the question correctly, but whoever answered first tops it. Right? So in a way, it is like KBC, Kaun Banega Crorepati. So this is what the landing page looks like. So you have quizzes and tournaments. So tournament consists of 8 to 10 quizzes, and you can select a quiz. You can choose to register in that quiz, and during the day of the quiz, you'll get notifications saying, hey, this quiz is about to begin, you should join the quiz room. Okay? So this is a pretty simple, the landing page is pretty simple, straightforward. Shows some stats about who won the previous quizzes, how many points did they score, all that. Nothing too complicated here. Okay? So this is the landing page. This is a simpler application. Then we have the actual quiz room or the quiz application itself. Okay? So this is what the quiz application looks like. So you have a question and the timer is counting down. Okay? So the timer there is counting down. On the right, top right, you have a YouTube live widget, so YouTube video. There is a chat window, YouTube chat, and a leaderboard. And now you can select an answer. As soon as you lock in the answer, it's submitted, and then you can't change the answer. We don't show the results until the timer expires, because obviously that would give an unfair advantage to others. So now when the timer expires, we show the statistics. Okay, how many people answered correctly, how many answered wrongly, whether you answered correctly, did you rise or fall in the leaderboard. Right? So straightforward. But there's a lot happening behind the scenes. Now, like I said, this quiz application gets exercised for 20-25 minutes on Wednesdays, Thursdays, and Fridays. So the sum duration is like 75 minutes in a week. Okay. So what does our workload look like? This is what the workload looks like. It is basically flat, but on the day of the quiz, we get a 50,000x rise in traffic. Okay, so this is my API, Azure function, which is sort of like lambdas, if you will. So this the APIs not exercise much. So the only activity that happens is people register for quizzes and tournaments. That's hardly any activity. But on the day of the or at the time of the quiz, they are submitting answers. They are requesting leaderboards. There's a lot of API activity that's happening. So this is the sum like of API executions. So you can see that these are extremely spiky, right? So this is the API. Now the DB also exhibits very similar characteristics. Now obviously when the API gets active, like you hit the API endpoint, obviously it's going to go interact with the DB and fetch or write some data to the DB. So the DB also exhibits a similar characteristic, right? It's very spiky in nature. When the quiz is happening, we have spikes in activity. Otherwise, it's pretty much flat. Same for WebSockets. So we use WebSockets, or rather Azure's Web PubSub offering, to transmit the leaderboard and the questions and the right answers to the users. So when you're playing inside the quiz application, the data that is shown on your screen, the questions that are coming in, it's not coming in through a REST API, it's actually coming through WebSockets in a encrypted format. That also exhibits a spiky characteristic, right? There is hardly any outbound traffic when on non-quiz days. Other than that, it's spiky. So now we've looked at APIs, DB, WebSocket activity, all spiky in nature, all exhibits similar characteristics. So this, when the general rule of thumb is when the workload is spiky in nature, do not reserve capacity, do not provision an app service, or do not provision a Kubernetes cluster, go for serverless. Because it's a pay as you go. You only want to pay for that 75 minutes of activity in a week. You don't want to pay 24/7. So which is why we use Azure functions for our APIs. We use Azure CosmosDB serverless tier for our this thing, and Web PubSub is anyways a pay as you go. So, well, for all intents and purposes, I'll get into the nitty-gritties. So we'll cover some guiding principles. So most of the application, we borrowed this from the book Microservices by Sam Newman, Building Microservices. It's a very good book. I highly recommend that. 12-factor app. So if you don't have time to read the entire book, you can read this. You can go to this website called 12-factor app. It was written by the Heroku folks. So they laid out the principles. If you have to develop an application in in a microservice way instead of a monolith, what are the 12 factors to pay attention to? Things like externalized configuration store, self-bootstrapping applications, like how to do coordination versus choreography, things like that. So nothing out of the ordinary here. Okay. Other thing we had to pay special attention to is the limits quota. So we end up using pretty much every single Azure service under the sun. So we had to, this is a highly scalable app, so we had to pay attention to the scalability limits. So if you are using a storage account, what's the ingress and egress limits? At what, when beyond what threshold are the caps applicable? So things like outbound traffic, when does it get throttled? And at what capacity? So there is a, I'll be sharing this slide deck so you can take a look at that page. All right, so this is what the application architecture looks like. Okay, it looks very busy. It looks like there's a lot going on, but I promise you, every single component in there serves a purpose. Okay, so the website is called quiz.confub.com. Okay, so just to set some context here, confub.com, the parent website, is a pre-existing conference ticketing management website. And that's already been done in AWS. It's done years ago. Okay? So we had to develop this quiz component in Azure, primarily because Microsoft was sponsoring it. So we had to do it in Azure, and we're getting free credits. So this quiz component, or this quiz child application, had to be done on Azure. And we had to somehow retrofit this on top of the user pools and the DNS entries that Confub already had in AWS. Okay? So it was an interesting challenge. So let me walk through all these pieces, right? So busy diagram, lots of components there. So let's break it down piece by piece. So let's start with that. So this is entirely, we don't have a native mobile application. It's entirely browser based. So whether you're playing on laptop, desktop, mobile, you are going to load up the browser, Chrome, Firefox, whatever, and use it, Edge. So all the players will log in through their browsers on their devices, and then they go to their website, quiz.confub.com. Okay? That brings us to AWS Route 53. Now, why AWS Route 53 and not Azure DNS zones? Now, this is because the parent website, confub.com, is already being managed in Route 53. So all our subdomains we had to retrofit into Route 53. So basically, these are CNAME records. So quiz.confub.com will redirect to some CDN endpoint in Azure. That's what's happening next. Okay. So we have CDN endpoints. Now CDN obviously great for serving static content like your HTML, CSS, JavaScript, minified JavaScript files, any static files like like background music or images. All of those, CDN is amazing because caching at regional POPs. Azure has some 54 locations, so you don't have to. If you are located in Southeast Asia, you don't have to go all the way to West Europe. You can load it from the local regional POP. Broadly compression is available for by default. So things get compressed to up to 40% of their original sizes. And then manage TLS certificates, right? I don't want to worry about Let's Encrypt or managing. So this is a self-managing. They provide self-managing TLS cert, so I don't have to worry about renewals as well. And URL rewriting rules. So you can modify the response, attach some headers, like we use it for cache control and stuff, and I'll walk through those details. So two sets of applications. Yeah, there is a landing page, but that's minor. So really we have two big applications. So one is quiz.confub.com, which is the main quiz application, which all the participants play. And then there is quizadmin.confub.com, which is where the quiz creator uses to create the quiz, choose the order the questions, choose the answers, all that, and how much time limit is on each question. So all the policies are set at in this application. They're all React.js applications, and they are put in storage account. So they are served out of a storage account with static site hosting. Okay? So the flow on the front end is pretty simple. User hits the URL, goes to Route 53, goes to the CDN endpoint, goes to the storage account, and from the storage account we load everything: HTML, CSS, JavaScript, all the static images, everything, the music files, everything gets now it's in the user's browser at this point. Okay, and this is where the application will take over. Now all the calls will first go to the API gateway, or what we call in Azure API management. So all our endpoints are here. So everything goes here, and this is where we aggregate and centralize all our policies like JWT validation, rate limiting, CORS, caching policies. Everything is aggregated here at API gateway level. Okay. So the first thing it does is now obviously you have to be authenticated. So the first thing it has to do is it has to fetch something known as the authority and audience. Basically what happens is all the calls, there is an authorization header with a bearer token, JWT if you will, and we have to decrypt the JWT to see that this JWT is actually intended for whom it is intended. It's issued by whom it says it is issued by. So those validations have to be done. So we know who issued it, we know who it is intended for, the authority and the audience, and we stash that away in a key vault. So when the call comes in, the first thing it does is fetches those values from the key vault, and then it talks to AWS Cognito. The AWS Cognito, being an identity provider, has an OpenID endpoint. So we cross-check the authority and audience of the JWT against that this thing. We check whether the signature matches, whether the token has not been tampered with. So all those checks happen at Cognito level. Now the question is, why Cognito? Why not Azure AD? So remember, the parent website is quiz.confub.com. There are thousands and thousands of users already in that Cognito pool, and we want to use those same user identities. We don't want users to recreate their profile page all over again. So we just decided to reuse that AWS Cognito pool, and we ended up using Cognito as our identity provider as well. So that happens, and now we are authenticated. And then what happens is, now this is the API, and for some frequently asked, API endpoints with high rate of requests, we cache them in Redis Cache. So again, the integration between API gateway and Redis Cache happens through a XML policy. It's pretty straightforward. So for something that is hard to compute, or something that is accessed very, very frequently, like question 15 is over, what is the leaderboard? That's a very frequently asked question. We just stash the answer in the Redis Cache. So and it's served out of there. But for stuff that is not cached, now we have to actually go into the API. So we use Azure functions for all our API. So basically these are HTTP triggered APIs. So the first thing we do is we don't execute the request straight away. We queue the requests up, right? So thousands of users, hundreds and thousands, thousands and thousands of users are submitting their answers at the same time. So we don't process them straight away. We queue it first and foremost. So this goes into a service bus. And then from the service bus, it is dequeued in batches, right? So we dequeue it in batches of, I think, like 200 or something like that. And then we process the batch. So what happens is, this is a pattern called queue-based load leveling, and irrespective of the rate of incoming requests, you're always going to process 200 at a time. So it levels the load on the server side. So that way it doesn't overwhelm the database. Okay. So then obviously it stores all the, computes the leaderboard, stores it in the in CosmosDB. Basically they are JSON documents. And then we have a trigger set on CosmosDB, so which essentially says, hey, this leaderboard has been updated. Now I need to update all the users, that their positions went up, their positions went down. So that has to be done in real time. So we have a trigger set on CosmosDB. So every time a quiz, question, or a tournament leaderboard gets updated, the Azure function wakes back up, and then it uses Web PubSub, which is basically a fancy way of saying a WebSocket server. And we send the leaderboard there, and we basically AES encrypt it, we send it, and then Web PubSub does all the heavy lifting of maintaining the client connection, maintaining resilient connections, establishing connections when the connection drops. All those things is handled by Web PubSub, and then it sends the thing to the player. So when at the end of the 30 seconds, when the screen flashed that, hey, you answered correctly or you answered wrongly, 55% answered correctly, 30% answered wrongly. So that statistics all comes from Web PubSub, WebSockets. Okay. So this is the end-to-end flow. There are a couple of other components, like we use Azure Monitor and Azure App Insights for all telemetry tracking. The app is very heavily telemetrized. So we track metrics at user activity, we track all system health, all that is done. We have alerts and metrics. We have metrics, and we raise alerts when a metric goes beyond some threshold. And then we have dashboards to visualize it. But we really mainly rely on the metrics, on the alerts to inform us if something is wrong. And then we have the CI/CD pipeline. So everything is in Azure repos. On check-in to main, the pipeline gets triggered, and then the pipeline goes ahead and deploys everything. So that's straightforward. So this is the, so I said that every piece has a purpose. So here we are. Okay. So this is great, but this doesn't explain the scaling challenges. Now I said that this app can scale to 100K users, but in reality, I think the maximum number of players who ever played it is, I think, like 32,500, I think. So we haven't tested beyond that, but I'm pretty sure it will scale up to 100K, and I'll get into why 100K and not beyond that. So what are the scaling challenges? So now let's look at all the components piece by piece again, and then identify what are the scaling challenges in each of those components. So nothing in this part, we are all good here. Nothing at the DNS. DNS resolution happens very fast in Route 53, no issues there. No problem. CDN, this is where it gets interesting. Okay. So we use CDN, what is that? CDN Classic. No, we don't use Azure Front Door yet for cost reasons. We are using the Microsoft CDN Classic. So one of the things is it only offers compression when the file size is less than 8 MB. So this really means you really have to minify your files. But even with minification, often the file size can grow beyond that threshold, especially when you have a whole bunch of NPM packages that you rely on. So remember, it's a React.js application. So what we end up doing is we end up chunking the file. So we use something called as chunking. If you are using Angular, you can use lazy loaded modules, and that way each module size will be small. If you are using React, just use chunking. Just ensure that pointer isn't working, but that's okay. So on that size column, just ensure, is this visible in the back? Can you see the numbers? So just ensure that the size of each chunk or each file is less than 8 MB, and you're guaranteed that it will be compressed. You will get Brotli compression enabled on it. Okay. So you can see that content encoding BR. BR means broadly compression, and that's what's written in the response header. Right? So rule of thumb, make sure file size is less than 8 MB if you are using Microsoft CDN Classic. Okay? Second thing is, people, especially when they're playing on mobile, they tend to flick their fingers up and down, and that causes a browser refresh, right? Like when you swipe the finger down, that actually refreshes the page. So we, in our telemetry, we found that a lot of activity is just F5s, pages getting refreshed. So when the refresh happens, we didn't want to go all the way back to the endpoint. We didn't want to go all the way back to the CDN also. Can we cache it in the browser so that it gets loaded from the browser on a refresh? The answer is yes. But the content that is served out needs to have a cache control header. So we enable this cache control header through the CDN's URL rewriting rule. Okay. So essentially what we do is, there is this thing called rules engine. You just set a this thing, cache expiration header. If it's missing, just set it to 1 hour or something, which is more than enough for the duration of the quiz. And then whatever image file or HTML file comes out, the next time you hit F5, it's going to get loaded from the browser itself, right? Because the cache control header is set. So now in this case, so you can see that everything is cached, and on refresh, the latency is 0 milliseconds. It's because it's loaded from the browser itself. Okay, it doesn't have to go back to the CDN to load it. So that was a good optimization, saved a whole bunch of traffic ingress. Okay, so those were the things, and we were good with the CDN. Next component, storage accounts. We didn't really have much challenges with the storage account. Everything worked fine. The ingress and egress limits, we are always underneath it. And even if you overflow the egress limits, you don't get rate limited. You just pay a little bit extra. So we were fine with that. Now comes API gateway, and this is fun. So one of the things that happens is, because we have CORS policy enabled, the browser will keep sending pre-flight options request, and it keeps doing that. So we wanted to cache the response. So if a pre-flight request has been accepted, we can just return that. You don't need to like revalidate that pre-flight request. So what we do is, we set a policy called pre-flight request, allowed method, and we set the pre-flight result max age to 300, which is 5 minutes. So in that 5-minute window, if a pre-flight request is generated again, we just return the cached response. Okay. We could increase it, but 300 I thought was reasonable enough. So now you can see that the options request is just getting served out. It's the cached one, and the cache, the access control max age is now set to 300. Other thing is, we realized the hard way is, we have this tethered to application insights, or rather Azure Monitor. So all the requests that are coming in, we were logging it, and at the rate, the hundreds, like thousands and thousands of users playing it simultaneously, that was just overwhelming the ingress. So what we did was, we set the sampling rate, instead of 100, we changed it to something like 95 or something. So that eased a bit of pressure. Okay, so we change the sampling rate. Never set it to 100. Just make sure that you set it to 90 or something like that. You will lose some samples. You are not going to lose the request. You are just going to lose the request logs, and that's okay. Completely fine. After that, we were done with the API gateway. Key vault, no problem, no challenges there. And Key Vault, you access it only once when the application starts up, right? That is where it starts up. It's a self-bootstrapping application. It wakes up, it reads the connection strings and the endpoint URLs from the Key Vault, and after that, Key Vault is basically not used again. Cognito, no challenges. Redis, Redis was interesting. So obviously, you want to cache your most expensive calls. Like if something is like really hard to compute or has a long latency, you don't want users to keep hitting that endpoint again and again. You just want to cache those requests. That's what Redis Cache is for. So we set the cache for the cache expiry, or basically the eviction, line item eviction, for 120 seconds. So after 120 seconds, the item is evicted. So why 120 seconds is because, okay, so when you're playing a quiz, the question is valid for 30 seconds and you have a chance to answer that. So what we were finding is that people were creating multiple accounts, and from one account they were answering it, and from another account they were checking the leaderboard to see whether they answered correctly or wrongly, whether their position has come up or come down. And then if they found out that they were answering correctly, and then from the other account, they would submit the right answer. So they were gaming the quiz. So we decided, okay, we need to cut that out. So we just decided to show, when the quiz is in progress, we always show the cached leaderboard. So you might see something stale, but after all the 15 questions are over, the leaderboards will catch up, and then you will see the real-time updates. While the quiz is in progress, we cache it for 120 seconds. 2 minutes, basically. So what that looks like is when you request the leaderboard, it will say that cache control max age equals 120. Right? So what happens then is, once we put the Redis cache in place, the number of cache hits were far greater than the number of cache misses, which means we are always serving it out of cache. So which is a good thing. That meant that the spikes that were happening, earlier they used to be pretty broad spikes, and now because of the cache hit, the spikes started becoming narrower. We can't completely eliminate the spikes, because the first time you request a leaderboard and it's not in the cache, it has to go all the way to the DB, and it has to fetch that. So that's an expensive operation. So you can't avoid the spikes, but we want to make it as narrow and as spiky as possible. Don't want to make it broad. So putting the cache definitely helped in that regard. So yeah, that's the DB's normalized RU consumption. And we were good after that. Functions. Okay, so this is the part where we queue up our requests. So what happened here? So again, this is Azure Functions. We are on the consumption plan for cost reasons. So we use the built-in scale controllers, event-driven horizontal scaling. So we don't tune it. It tunes itself. There's also, if you used an app service, you would have seen this rule-based scaling where you have to specify a JSON rule. We didn't want to get into that. We are fine with the event-driven one. So the thing to remember is the unit of scaling is the app itself and not the function. You can have 100 functions in a function app. When the scale out happens, you scale at the app level and not at the function level. So which means if your app scales to 20 instances, now you have, and each of them has 100 this thing. Now you have 100 into 20. Now you have 2000 total functions. Can your database handle that? So something to be aware about. So the rule of thumb is things that cannot scale together. If you have a HTTP triggered function and a service bus triggered function, then will they scale? Will they exhibit similar scale characteristics, right? So things that don't scale together don't belong together in the same function app. Okay, so the exception to this is service bus, where if the service bus queue size goes beyond some threshold, it spawns up to 32 instances within a function app. But that's a caveat. One thing to do is enable the scale controller logs. So basically all you have to do is go to the application setting and put this thing called scale_controller_logging enabled, and set that to that app insight's verbose value, and you get something like this, right? So this is a Kusto query, KQL, that you can use to figure out what the, like how many instances of your apps are currently in flight. So the previous count here was 0, now the new count is 0, which means it indicates a scale in, which means traffic has dropped, now it has scaled it back in. Okay, so the final point is important. So every scaled out instance, right, is basically starting from cold start. So every time, let's say you have one instance, and now because of the increased load, now you have two instances. The second instance that just got created is incurring a cold start. And if it is talking to a CosmosDB or some repository, the connection string, basically the connection has to be instantiated. So there is some handshake overhead there. So something to be realized. If you're on the app dedicated plan or on the premium plan, you can use something called as a warm-up trigger, which means the scaled out instance is only available to serve traffic once it has been warmed up by that warm-up trigger with the connections instantiated. So use that if you can. So we, in our telemetry, we noticed this, right? So our P99 latencies, most of our API calls within 550 milliseconds. Now I don't know if you can read that, but most of the traffic was served out within 550 milliseconds. But then there were some outliers which took up to 6.8 seconds. So what happened there? Why did those incur such a heavy overhead? right? What caused that bigger latency? 6.8 seconds. So the answer there is, now this is our end-to-end transaction tracing. At the API gateway, request comes in, talks to function, and then invokes the Azure function, and then the Azure function has to talk to CosmosDB, right, to fetch some stuff. So between the API to function, we had some latency, and that was primarily because of the sampling rate. We had the sampling rate set on too high, so we reduced that, and then the gap came down. So A, we shrunk it down. But what was causing B, that long latency? This was, the cold started instance had to re-establish the DB connection. So what can we do to this thing? The actual DB operation, these small dots, they take 10 milliseconds, 15 milliseconds each. But this was taking around 4 to 5 seconds. So what can we do? So we decided to use the warm-up trigger there, right? Just the only way out. Then service bus. Service bus, not much scaling challenges. Earlier we didn't use batch triggers to dequeue, so we were dequeuing one at a time. So that felt, little too much. So we decided, okay, why not dequeue it in batches? As long as the batch size doesn't overwhelm the database, we are doing that many number of concurrent writes, right? So we the sample from GitHub itself, right? So you can we use Azure functions, service bus triggered functions, and you can essentially specify if you use POCO binding and serialize it to an array, so service bus received messages, you'll get a batch of messages instead of individual messages. So this is how we process it, basically. So one of the things is now we are getting it in batches. So you have to use the unit of work or a transaction, basically, to make sure that all the batches get committed at the same time. So unit of work pattern has to be in there. So you basically can also play around a little bit with the host.json to see how many, this is basically where you can set the batch size and all that. So those are details we can probably skip. Okay. After that, we were good. Okay, now on the this thing. When we were dequeuing it, one of the things we realized is because of the scale controller, it can scale it up to 200 instances, right? So in a consumption plan, you can have up to 200 instances. So that many number of scaled out instances can tend to overwhelm the database because CosmosDB is what it's ultimately talking to. So one of the things you can do is when you under that scale out tab, you can say enforce scale out limit, and you can say, hey, I only want one listener there. I don't want competing listeners. I only want one, and it's fine. So we set the scale out limit there. Okay. In reality, I think it's like more like five max five scaled out listeners. After that, we were good. CosmosDB. Okay. Okay, we have 5 minutes. So CosmosDB was very interesting as well. CosmosDB, if you're doing anything with CosmosDB, start with the capacity calculator, right? So you know what your document size is. You know how frequently you're doing. Is it a read heavy or a write heavy workload? Is it a multi-regional operation? So all those things, right? Is it a point read? Is it like a full table scan? When you can estimate the cost of all that. So start with the capacity calculator always. Beware of hot containers. So with provision throughput, we started with provision throughput and we used shared database throughput, and that was a mistake because that doesn't distribute the load, proportionally. So what ended up happening is we had two containers that ran way hotter than the others, right? So this is the throughput on the exercised by the two containers. So basically, the tournament leaderboard and quiz leaderboard, because they are being updated in real time. So those things, those containers ran hot. But the problem is because of the shared database throughput, the provision throughput was not getting through to them. So we had that problem. So prefer dedicated container throughput if you can. Don't raise the throughput too high because then you will have it retains some memory. You will not be able to scale it back down, and this happens. I think like it remembers what the max ceiling was, and then you can only scale it back to 0.1 of that max ceiling. So If you raise the throughput too high, you can't come back to the previous level, at least in one step. So something to be careful about. And then other minor things like, we switch to serverless tier. So it's good, but you have to be aware of all the caps at the partition level. So there is like a 5K cap, max RUs per container cap. And what else is there? There's no regional replicas, but we are okay with for now. And you can drop unnecessary things from the index, right? Like we had this large leaderboard with all the arrays, and they are not being used in search or any of the where clauses. So you can drop them from the index. So that brought our consumption down. And after that, materialized. Okay, so because this doesn't support materialized views, we have to put CosmosDB triggers. CosmosDB triggers adds throughput pressure. And then other thing is scale out this thing. So the more you scale out an application with CosmosDB triggers, the more the pressure will rise. So it becomes like a death spiral, right? So we had this thing increasing from 27 to 41 in a few seconds, and then that just kept increasing the count, the RU consumption count up and up. So it went into a death spiral there. So again, you have to enforce the scale out limit there for that very reason. Okay. And, PubSub, it's a mess, and that's partly because I haven't fully wrapped my head around it, how to, what's the correct message size, message frequency, outbound egress limit, all that. Like I have to wrap my head around it. So right now, this is my expression when I look at the pricing calculator. Someday I'll figure it out, but for now it's a big question mark. I'll figure it out someday. But this is suboptimal, the way I have implemented it at least. I'll work on it someday. And monitor, this is what it looks like. All the errors, errors, exceptions that are happening, we view them in near real time. Then application map is, we can identify all the hotspots that are in our application. And again, we talked about the P99 latency and stuff. And DevOps, again, we have a test environment and a prod environment. Release to test happens automatically, release to prod happens with manual approval. There's a manual approval workflow. So that's it, it's that simple. Right, that's my email address. Feel free to, get in touch with me if you have any questions. Thank you, everyone.